Thank you. Good afternoon. I come from Metz in Lorraine, in the northeast of France, and I will speak about oxygen vacancies, and especially about the possibility of detection of oxygen vacancy in strontium titanate by Raman spectroscopy. So, 3 keywords in my talk: strontium titanate, example of antiferrodistorsive phase transition and quantum ferroelectric, oxygen vacancies, which are very important for application concerning, especially for electrochemical and electrical damage. It's also important for doped strontium titanate, as we have seen just two talks before. And Raman spectroscopy, which is an efficient tool to study phase transition. So the main question of my talk is Raman spectroscopy able to probe oxygen vacancies? 10 years ago, Tene and co-workers have investigated the effect of reduction of the Raman spectra on strontium titanate. They found new lines which are indicated by red square, and they attributed these new lines in the Raman spectrum to oxygen vacancies. But we have noted that these lines are located at the same, nearly the same position as in the iron doped sample. And is the case in the thin films, single crystal or nanocrystal. So that means that probably these new lines could be attributed to iron and oxygen vacancy pair. So is the reason that we have decided to reinvestigate by Raman spectroscopy the question of oxygen vacancy in strontium titanate. For this, we use 2 samples, one untreated sample and one reduced sample. And for the reduction at a high temperature under argon atmosphere, and we have estimated the deficiency of oxygen to 0.5%. So what is important in our studies that we use the same source of material for 2 samples in order to avoid any contamination by impurities, and particularly for iron. So we investigate by Raman spectroscopy with exciting laser at 633 nanometer, and we make measurements on cooling from room temperature down to 93K, so just below antiferroelectric transition. Also, in order to corroborate our results, we applied principal component analysis. It's a statistical method used to classify data. So first, I show you the results obtained in untreated samples. So the Raman spectrum is relatively complicated, and you see here the evolution with temperature. We can see the peaks level 1, 2, 3, and so on, which are well known and attributed to second order scattering, and the R lines, which are seen in the low temperature, are due to antiferrodistorsive phase transition. I remind you that, in principle, first order Raman scattering is forbidden in the cubic phase. So we have no additional line. It means that it's the proof that we have a stoichiometric undoped crystal. Now we go to the comparison between untreated and reduced sample for the same temperature below AFD transition. So we observe the same peak in both samples, but additionally for the reduced sample, we see new lines noted A, B, and C. We can point it out that our spectrum is completely different from this reported by Tene and co-workers 10 years ago. If we look at the temperature dependence of the Raman spectrum in the reduced sample, the new lines A, B, and C increase in intensity on cooling. But the position is relatively constant as a function of temperature. So we have detected 3 new lines, A, B, and C, and these lines are enhanced by reduction, treatment, and cooling. The question is how to distinguish the on effect of reduction, so that means occurrence of oxidation vacancy, from the effect of the temperature on the Raman spectrum. For this, we use principal component analysis. It's a statistical method which can provide the relative change of a spectrum compared with the mean spectrum, if you make an average of all spectra or all data. So that means that the spectrum can be expressed as a function of the average mean spectrum and as a function of principal components. And principal components give idea about the variability of a spatial spectrum. Here, S1 or S2 are the contribution of the spectrum to each principal component. S is are called score or weight of the principal component. So I can show you the results with this analysis. We took all data, so that means untreated and treated samples, and what we observe. You can look at this 2D picture. The mean spectrum is at the origin. Here you have on the upper part the spectra or the data corresponding to the reduced sample. And in the lower part, all data corresponding to the untreated. So you have a clear separation between both series of data. Another important point that if you look at, for each series of data, if you look at the temperature change, you can see that you have from the right to the left a decreasing of the temperature concerning the data. That means that if you look at principal component number 1 or number 2, the number 1 it corresponds to the effect of the temperature for both samples. And concerning PC2, principal component number 2, is the effect of the reduction of the treatment. And you can see that the reduction gives a more effect if you are at low temperature. So we have a clear separation about the effect of temperature and the effect of the reduction by this analysis. Now, if you look at the loadings, so we can see here on the upper part the experimental data at low temperature, and here the loadings for PC1 and PC2. In PC1 you have, I remind you, is the effect of temperature, and you have the part here, the part of the spectrum which is particularly sensitive to the temperature. And here you see is due to the second order scattering, if you come back to the Raman scattering. If you look at PC2, PC2 is the effect of reduction. So these peaks in red corresponds to the part of the spectrum which are affected by the reduction. And you can see that these ranges nearly corresponds to the new lines A, B, and C derived from the comparison between untreated and reduced sample. So that means that we have shown by means of the comparison and principal component analysis that the new lines A, B, and C are related to oxygen vacancy. Now the question is, which is the real origin of these new lines? Because I remind you that, in principle, in the cubic phase, no first-order Raman scattering is expected. First observation that these lines are located at the same position as optical phonon deduced by hyper-Raman data in the cubic phase. So that means that these lines correspond to first-order lines of the stoichiometric lattice. And these lines are, in fact, activated by local symmetric breaking due to oxygen vacancy. So, the effect cause local polar regions with diameter called L here. So this cluster or polar region have a tetragonal symmetry. So that means that you have a breaking of Raman selection rules, which can induce the observation of first-order lines. Another important point is that this cluster around oxygen vacancies are also responsible for the asymmetry of some lines. I will show you how in a few. Due to the local symmetry breakdown, not only the optical phonon at the Whirlwind zone center can be activated by defect. Here you have the frequency as a function of the wave vector. Here, the zone boundary. So you can, due to the defect, you can see by Raman phonons with different wave vector. And we can use for the model initially proposed by Richter concerning the intensity of first-order Raman line. This model is more and more used now for nanostructure. Here you have a Gaussian distribution which depends on the dimension of the nanocrystal or the cluster. A is the lattice parameter. Gamma is the line width for stoichiometric material, and omega q is the phonon dispersion. And you make a summation on q star. Q star is the reduced wave vector. It means in units p over a lattice parameter. So if you have large L, means you have no defect, you find again the Lorentzian shape. So which are the results with the model? It's shown here. So you have here the experimental data, and we look at this line, A line, and we make calculation with L1 equal to 20 lattice parameters. So that means that you have nearly stoichiometric crystal. In this case, you have the red line shape, so a symmetric line. By contrast, if you use L2 equal 4A, that means that you have many defects, many oxygen vacancies in your lattice. With the calculation, we obtain the blue shape, and you see that the position, maximum position, is nearly the same, but you have a broadening on the upper part of this line. So that means that the asymmetric line shape of this line is due to cluster around oxygen vacancy, and also due to the relaxation of Raman selection rules. So I go to the conclusion and summary. So the main question I have is Raman spectroscopy able to detect oxygen vacancies in sodium tantalate? I can answer yes, we can do it, and with a relatively good sensitivity, because we detect 0.5%, the effect or the influence on 0.5 deficiency of oxygen, 0.5%, of course. But it's necessary to check if you have no other source of point defect of impurity, because this kind of defect can give rise to the same induced line. And we have seen these oxygen vacancies by activation of phonons on the win-win zone, and not only to the at Q equals 0. For the next future, we want to confirm our model concerning the link between the cluster size and the oxygen vacancy concentration by measuring the different reduction ratio, and to look at the degree of asymmetry we can obtain by a Raman spectroscopy. Okay.
Thank you
for your attention.
Thank you very much, and the paper is open to questions. Yes, please.
Without microphone.
Okay.
Closer. Yeah.
So first question, these were single crystals.
You should.
These were single crystals you studied. Single crystals.
Yeah.
Okay. So my question will be, can you measure do similar things on polycrystalline samples? Can you measure this Raman spectra, similar Raman spectra on polycrystalline samples?
Yeah, of course.
So you get the same results?
Additional lines due to grain, because grain creates some stresses and so on. And if you have stress, strain is something like defect. So it means that you have a breakdown of Raman selection rule, and you can have additional lines. So it's more complicated.
Of course, strontium titanate was studied many times as a function of oxygen content with respect to conductivity and other properties. So are these samples transparent, or they are black after reduction? So you didn't measure conductivity, but apparently they are very good conducting materials.
Yes, another question?
Yes, did you verify that the first two principles... Did you verify that the first two principal components explain most of the variance, and did you look at the patterns for the other components to see if there was any hidden features? Like component 3, because maybe it would reveal more features.
It's ready?
Or maybe it would be mostly noisy, I guess. Like, why did you limit to two principal components? Yeah, you can. Analysis will give you many. Okay, so it does explain most of the variance.
Any more comments? And yeah, very short. One of you only, and without micro.